Hey everybody, it's Tony from Adafruit, and hopefully that intro works. So I've got a whole new streaming setup, and as you can see, it's pretty crazy. I've got like a little retro terminal thing going on in the background. And today I wanted to talk a little bit about SPI, the Serial Peripheral Interface. And last week I had done a deep dive on the I2C protocol, so I think it makes sense to follow it up with looking at the SPI protocol using the Raspberry Pi. And we'll look at how to talk SPI using Python APIs, and maybe even look at a deeper level in Linux, how it's all implemented. But first, I'll give you a quick kind of rundown too of what I've got with the setup. So I upgraded everything. I'm using Wirecast now to do the streaming, so it's pretty fancy. There probably will be issues and things, so just kind of work through it as we go. But hopefully, I'll be able to do some cool stuff here. In the background, it's actually a little video that I shot from my desktop from Linux. It's this program called Cool Retro Terminal that gives you like a retro style CRT image. And then I'm running a little program called cmatrix that gives you the matrix effect back there. So I just kind of screen captured that and have it as a background. But everything else should be ready to go. So I've got main desktop kind of view. We'll come back to this in a little bit, and I can pop up also the head down here. And then I've also got a workbench view. So we'll see. And of course, we've got the logic analyzer, and it's not really in focus for some reason. Still working out some bugs and issues. But this is Raspberry Pi. Here's the Pi Zero, and it's connected to, I have both the ADS 1015 that we were looking at last week with I2C, and then also I have a little MCP 3008 analog to digital converter, but this one uses the SPI protocol, so we'll kind of play with that and investigate it. So let's see, so I've got that, and let's maybe jump back to the desktop view here. So real quick, kind of before I dive into the SPI stuff, last week I talked about I2C, and we kind of looked at, I left it at a point where I started to investigate using I/O control functions to talk directly to the I2C hardware on the Raspberry Pi, or at least the device driver. And I'd done some little prototyping with that and had a basic example. And this week I've kind of spun it out into a little library it's a work in progress right now. But it's basically a little Python library here. I called the Python Pure I/O, and it's meant to be a pure Python access to I2C and eventually SPI, maybe even GPIO. Just have to look and see what's available and kind of standardized on Linux. And the reason it's pure Python is because like that basically means that there's no native extension that you need to compile. You can just install this with pip, and it just uses Python libraries to talk directly to the hardware. Because the big problem I was talking about before with the I2C, the Python SMBus library, it's sort of maintained. It's a little hard to find the owner. It's not Python 3 compatible, so it's a bit of a pain to deal with. And if you make a pure Python version of that, then it's a little bit easier. You can make it work with Python 3. Might not be as performant. There are trade-offs to these things. So this is a link. It's on our GitHub repository. It's the Adafruit Python Pure I/O, and once this video is on YouTube, I'll put in the description links to all these things too. I kind of put a note here that this is a work in progress, so it's definitely not fully kind of ready to go yet. But it's a good example if you just kind of want to check it out and see how I'm using I/O control and C types. So I basically fleshed it out, and I have an SMBus class that's a direct copy of what the Python SMBus library exposes. So all of the same functions, like reading a byte of data, I've re-implemented those using I/O control functions against the I2C hardware. And so I have some little helper functions that make it easier. It turned out to not be as difficult as I thought. Like, let's see, this is only maybe 300 lines of code or so. There's one function I didn't implement yet because I actually have to get in at a much lower level, and the I/O control stuff doesn't work. I have to use a different I/O control function, but it's not a really commonly used function. It's reading a block of data, which it sounds like it's important, but it's a really weird format where a block of data, like the first byte, indicates how much data is going to be read. And I don't know of any I2C devices that use that, but I'm sure there's stuff out there. I mean, there's a reason they added it. But anyways, though, so it's a good example to kind of look at. It does work, so I'll kind of, we'll jump to the Pi. So I swapped over my GPIO library that all of my Raspberry Pi libraries use, and I made it use this new Pure I/O for SMBus, and it was just a direct swap. So like in the code, I'll actually show you. So the GPIO library code for I2C So previously I was importing SMBus, which this is the Python SMBus module that we looked at before, and I just swapped it over to import my new PureIO SMBus and just renamed it the same thing. Didn't change anything else in my code here, so it's calling all the same functions, like read byte of data, doing the same transformations, and it actually does work. Now it's a little unstable. I ran into a problem. I need to debug a little more. But if I go into the Python ADS and the examples, and if I run the simple test, so this is actually outputting data. You can see it just exploded. It at least got 2 readings. So it's something funky about the format of the data I'm returning, and it's working sometimes. I have a feeling like maybe it's getting like a null value somewhere, and my behavior is slightly different. So it's close. It's kind of coming there, and eventually, I'll kind of sort this out and have this available as a little pure Python library, because I'd like to eventually move all of our Python libraries to depend on this pure Python implementation. So that way it can actually work with Python 3. We have a little more control over it. We can add more functions to it that we need. And it's easier to install, so you don't have to have like the Python developer tools and things ready to go for it. So that's just a little update on that. So what I wanted to talk about for this stream is looking at the SPI protocol, the Serial Peripheral Interface Bus. And so SPI is just another way for a chip to talk to another chip. So it's a serial protocol, which means there's a clock that's driven to kind of synchronize how the 2 chips talk to each other. And like last week, we looked at the I2C protocol, which is a neat little protocol. It just uses really 2 main lines for the data. There's a clock line and a data line. And it has a concept of addressing, so you can have like up to 128 devices all just sharing those 2 lines. Now the SPI interface is a little bit different. So it's it's still a serial protocol. There's still a master who controls a clock, but it actually has more lines of data. So there are 4 lines that you primarily deal with. So there's the clock line still. There's also a chip enable line, which kind of tells a chip that it's going to receive or send SPI data. And then there's a data out and a data in line, kind of like a serial protocol. And unfortunately, they're always a pain because you need to kind of think about, okay, from whose perspective is that data an input or an output? And so sometimes you see like MOSI, master out, slave in, or MISO, master in, slave out. And in that case, the master means the clock master, like who's actually driving the SPI bus clock. And with the Raspberry Pi, in almost all cases, it's the Raspberry Pi itself. Like when they're talking to a peripheral, the Pi has to control the SPI bus. So in that case, the data output would be the Pi outputting data to a chip, and the data input would be reading data from a chip to the Raspberry Pi. And so we'll kind of see that as I look through, as we look at more of the examples and things here. But the Wikipedia page is, again, it's pretty good just to kind of skim and get an overview about the protocol. So it talks about, at a physical level, how it works. It's, really just those 4 lines. Now, the one big difference with I2C is that each chip needs an individual chip select line that goes directly to it to talk to it. So if you had like 4 devices that use SPI and you wanted to talk to them using a Raspberry Pi, you'd have to have 4 different chip select lines, because each time you want to talk to a chip, you have to toggle its chip select line. And so you can't have multiple chips sharing that, or else they'll get confused and they'll see that, I'm being told that I'm having something, sent to me, but I don't understand it. So that's one big difference. Another important difference is that the master has a lot more control in the SPI interface over things like the clock speed. I don't know if the protocol actually has any limits on the clock speed. It can go well into the upper megahertz. The Raspberry Pi supports, I don't know what the slowest speed is. I'm sure it's like maybe down in like the kilohertz or so. You can actually find the BCM 2835 peripheral reference manual. That's kind of the definitive reference of all the peripherals on the Raspberry Pi. I'm sure it says like what the limits are for the SPI hardware, but it can go up to I want to say around like 20 megahertz roughly, maybe if it's overclocked. So that's pretty fast. The I2C was only 400 kilohertz, so you can send things a lot quicker with the SPI interface because you have control over that clock. And so that's kind of one of the big things that's different about it, is having that control over the clock, and each device has to have an individual chip select line. The other thing, and we'll kind of look at this, we'll look at the logic analyzer and kind of look at on the wire what things look like. But there's also a big concept of polarity and phase. And this kind of comes down to, you might see it referenced as the SPI mode. And so this controls how the chips interpret the SPI bus data, like if the clock should be high or if it should be low when it's active, or if you want to sample data on the rising clock edge or the falling clock edge. And so those two different bits, two different states, you can kind of change independently. So there are 4 different modes. So there's like SPI mode 0s, usually the default. I mean, every chip kind of varies. So yeah, sometimes you might see some differences. But with SPI mode 0, you've basically got the clock is active. It's active. When is it active? Is it active low? Inversion. Active state is 0. So yeah, wait. Let's see. Then polarity is 0. Oh, right. So polarity is 0. The clock is at a low level, and it goes high when it's active. And then when the phase changes, so that's when the data is captured and when it's sent. So when the phase is 0, then you're capturing data on the rising edge, and then you're outputting data on the falling edge of the clock. So it's something to be aware of. When you look at a device's data sheet, it should tell you what mode it expects to be in. And everything's different. Sometimes they're like, I'm in mode 0 or mode 4, and you kind of have to go back and map that to, okay, mode 4 means a polarity of 1 and a phase of 1. And sometimes the data sheets give you the polarity and the phase, so it's a little bit annoying sometimes to look at those different options. But I mean, ultimately, there's only 4 that you can kind of choose here. So let's actually look at on the wire what things look like. So I'll switch real quick to the desktop view. So again, I've got the Celia logic analyzer, the Pro 8 hooked up, and this time I have 4 of its inputs hooked up. So I have an input hooked up to the clock, the chip enable, the data output, and the data input line. And that's just connected to the little MCP 3008 here, analog to digital converter. So if we jump back to the desktop, and let's see, I'll put the workbench up in the corner too, so we can kind of see this. I'll go to the Pi, and we can run a little example on it. So let's go to the MCP 3008 library, and we'll go into the examples, and let's just run the simple test. And so this is a little simple test that's just going to read all 8 channels of the ADC. I think I looked at this in a previous stream, and so you can see as I change the channel, the potentiometer that's connected to channel 0, I cranked it all the way up. So this is a 10-bit ADC, so it goes from 0 to 1023, and I can crank it all the way down. And then the other channels aren't hooked up, so they're just getting kind of random noise. But you can see I have it hooked up using hardware SPI to the Raspberry Pi. So it's using the SPI's built-in, the Raspberry Pi's built-in SPI peripherals. And let's take a look then at the Celia logic analyzer program. So this is actually showing a previous capture, but what I'm going to do, so it's running in the background. Every half a second it's reading data from the ADC. So I'm just going to do a capture. It's a 2-second capture, and we'll just pull in all of these lines of data. Like we saw before, it kind of starts out zoomed out or zoomed in, so we'll kind of zoom out. So we can see each half second, there's a new kind of flurry of activity. And we'll zoom in here, and we'll go through all the different signals that we see for this. So let's see, maybe see if we can zoom in one more. Let's go out a little bit. Okay, there we go. So at the top, this one is the chip enable signal. And so you can see this kind of, it starts at a high level, and then it goes low when we're going to talk to the chip, and it stays low the entire time we're talking to the chip, and then it goes back high when we're done. The next one is the clock line, and so you can see this changes really quickly, and this changes every time data is sent or received over the SPI bus, and real similar like we saw with I2C. It also has a clock, like any kind of a synchronous serial protocol usually has a clock that's shared between the devices. The next one is the MOSI line, so the master out, slave in, slave input. This means the Raspberry Pi output, and it's the input to the MCP 3008. So think of this third line as whatever the Raspberry Pi is saying, anything it's outputting. And the fourth one is the master input, slave output. So this is the output from the MCP chip to the Raspberry Pi. So it's what the Pi is reading. Oops, I think it kind of moved out of the way there. So already you can kind of see, okay, so there's some stuff going on here, like the chip enable line gets pulled low, and that's just a part of the polarity of the device and the kind of the SPI mode. It controls whether the for some devices, they expect to stay in a low state and then go high. In this case, this device, it expects to be in a high state and go low. You can see the clock changes, and if we zoom in, we can see the frequency here of the clock, and it's about 625 kilohertz. It's close to a megahertz. So when I look at the code, you'll kind of see, I'm trying to set this for a megahertz, but sometimes when you're using like hardware SPI, you can't control the clock speed at a super fine granular detail. Usually it's like powers of 2, sometimes like a division of the main clock speed. So in this case, we're hoping to get a megahertz. We got 625 kilohertz. That's still pretty quick. That's good enough. And then we can see the output from the Raspberry Pi down here, and then the output from the MCP chip down here. And again, I've got set up in Celia's program. They have a little SPI analyzer. So this is really handy. You can configure this, and you just tell it which channels are hooked up to which I2C lines, and then it will actually go in and decode things. And so that's what you can see in the little blue parts underneath here are the values. And unfortunately, they kind of go away as you mouse over them. But this upper blue part right below my mouse, that's the output from the Raspberry Pi. And then the one down here, I guess right below the cursor, that's the output from the MCP chip. So you can kind of see, okay, the chip enable line is getting pulled low. The clock is cycling. So let's count. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So 8 clock cycles. That's a byte basically. So you can see I've effectively transferred 3 bytes of data here. And then the Raspberry Pi for the first byte is sending some data. So it's sending a value of 192. And if you go back to the data sheet for that device, you can kind of decode it and see there's certain bits you have to send to it to say, okay, I'm ready to take a capture and like which channel I want to capture. And then after I send that byte, you can see that the clock is pulsed, for 2 more bytes. And this time the chip is actually responding, so it's sending back a value, and this is just a numeric value of like 252 and then a value of 31. So those 2 8 bits of data, you have to put them together and you'll get 10 bits of data for the ADC output. And so that's basically one ADC reading that we see here. So it's a little bit simpler than I2C like we saw last time. Like with I2C, it had a whole concept of start conditions and stop conditions. You couldn't really tell which device was talking because they all shared the same data line, and so it was just whenever one device pulled the line low, it was kind of activating the bus. Whereas here you can actually see, like if I only want to look at the output of the MCP chip, I really just care about this 3rd channel down here, or the Raspberry Pi. I can kind of see that more in isolation. So a little bit easier to debug. But one big thing too, because it's running at a faster speed, I had to go in and crank up the sample rate here. So like before, I was capturing SPI or I2C at like 4 million samples per second. I cranked it up to 10 million samples per second just because I know my clock rate is about a megahertz, and so I want to make sure I'm at least twice above that to capture that signal. So you can see that's one SPI transaction, and if I kind of zoom out a little bit, you can see a few more transactions that kind of happen. And so there's actually 8 of these, 1, 2, 3, 4, 5, 6, 7, 8. And that just corresponds to the 8 different channels of the ADC. So the way this sample program works, as it's running in the background here, it's reading all 8 of these channels in a kind of sequential order. So this is channel 0, and then if I zoom in here, this is channel 1 that it's reading. And you'll see it's just kind of getting back like no useful data. This got back 0 values for that. It's basically just noise because they're not connected. And so then you can see like I've got 4 of these kind of little flurries of activity just because every half second, oops, zoom it out here, go all the way out. Come on, zoom out, there we go. So there's kind of 4 of these little flurries of activity. So that's kind of at a physical level how things are working on the wire. You can see it's a little bit simpler protocol, easier to understand, I think, than SPI, just because you don't have to understand, what's controlling the data line in this case. So next I was thinking maybe let's dive in and kind of play with Python, and I'll show you what are some of the libraries you can use to talk to the SPI interface, and maybe we'll look at, I'll actually do some coding, let's try out the different modes of the SPI communication, like let's send some bytes, see what it looks like on the wire, and how things change. And so maybe before we do that, I'll just kind of give a quick little overview about what your options are as far as talking to SPI devices using Python. So the big thing, the big library that I think a lot of people probably end up using is Spydev, the Python Spydev library, which is very similar to the Python SMBus library. It's a C extension that just wraps some Linux kernel APIs that expose the basic APIs to talk to SPI devices. Although luckily the Spydev library is a little better maintained. I think kind of in the last 6 months or so, I think some folks took over kind of ownership of it. So, there's recent code up here on PyPy. I think when they switched the Raspberry Pi to Debian Jessie and like the device tree overlays and things last year, that broke the old Spydev interface, and so luckily some people kind of came up and fixed it, and so it's awesome that people are maintaining this stuff. But this is the Python package index, which you might kind of consider this the homepage for the project. It mentions it's basically a modified version of some older code, and so you can go back and see that, and I don't think that code is maintained anymore. So this is kind of the current version. It's also on GitHub, luckily, so you can kind of see here's the actual code for it. And you can even jump into the module if you want and take a look at how it's all implemented. Very similar to SMBus like we saw before. This is just a Python C extension, and pretty much all of the functions, like if we scroll down and see, oh wow, you can see, so they're having fun. And this is kind of nice. Like luckily this library actually supports Python 3, but you can actually see some of the ugliness when you have to support Python 2 and 3, where you've just got if-defs here where it's like, okay, here's the Python 2 version and here's the Python 3 version, which I think that's a painful thing, unfortunately. It's just a fact of life with Python 2 and 3, but good to know at least this library supports it. But you can kind of see, okay, like here's the readbytes function, and it's really just parsing out the arguments, and then ultimately it's going to be calling like a read function, C function from the Linux kernel to read in new data, and then just kind of convert that to an output that it returns. So kind of good thing to explore if you're a little more familiar and you just want to see like, okay, how is Spydev implemented? Take a look at the code for this. If you search around and you search for like Spydev documentation, you'll probably find this PDF that someone put together, and it's actually pretty good. It's a nice little PDF, short and right to the point, and kind of tells you a little bit about the Python SPI interface. It tells you kind of how to get it installed and going on a Raspberry Pi. Gives you a little bit of an example for it. So here's like maybe a hello world almost of SPI communication. So you create a Spydev device, you open it up, and then you can just call certain functions. So like there's a transfer to function. This goes through and then actually talks about all the functions that are available and the different members you can use. So you can change things like the mode, like I was talking about before. So this changes like the polarity and the phase. But really, there's only about 4 functions that really matter with SPI. So you can read data, you can write data with write bytes, or you can transfer data, which is reading and writing at the same time. And there are 2 different transfers, and it kind of tells you the difference here in that it changes how the chip select line behaves. And maybe we'll kind of run these and see what happens with some Python code and look at on the wire how things work. So I don't know, let's just start. Let's just do this example and see kind of how this actually works. So I'm gonna go to the Pi and maybe let's cancel out of this, and let's make a new little program file. We'll call this spytest.py, and let's just copy out the source code from here that they show and see if this works. Oh wow, that's kind of weird. So I'm actually connected remotely to my Linux machine. I'm on a Mac right now, so hopefully this works. I'm using FreeNX, which is like a really nice little desktop sharing thing, and I'm screen capturing that. That's why you probably see at the very top this no machine thing, and this is just a little window. But anyways, it seems to be working. So all right, so let's paste in the code here. So okay, so we need to import the Spydev module. Oh, and by the way, before I get too far into this, maybe just real quick on how to initialize SPI. So the very first time you boot up a Raspberry Pi, using the Raspberry operating system, you probably won't have SPI enabled. So again, you have to go into Raspi config, and it's under the advanced options, and go through and click yes to all this enable the SPI interface. And it's going to want you to reboot. I'm just going to cancel out of this for now. But then once you do that, you can actually see the dev Spydev devices. So there's /dev/Spydev 0.0 and /dev/Spydev 0.1, and we'll look at kind of what those numbers mean in a second. But if you don't see these devices, it probably means you don't have SPI enabled, and if you try and run a program that uses SPI, you're going to get an error like file not found or IO error because it's trying to open one of these devices and it's not there. So real common stumbling block. I make that mistake a million times too, so it just happens. So for this Python code then, basically we need to import the library. Oh, and to install this library, you can just pip install it. So you can do sudo pip install Spydev, and that'll pull it down. It needs to compile a native extension. So anytime you need to compile a native extension on a Raspberry Pi, you need to apt-get install. It's just always safe to do build-essential. This will make sure you have the GCC compiler, all the basic Linux headers and things you need. And then you also want to install python-dev. So this installs the Python header. If you ever pip install something and you get an error that says, I can't find python.h, that means that you didn't install python-dev because it's trying to find the main header file that C extensions need to link to for Python. So first install those two, and then if you don't have pip installed, you can actually install python-pip, and that'll give you pip. And once you install all those prerequisites, then you can pip install Spydev, and that'll just do a quick little compile of its native extension and install it. And once you've got that all set up, then you can actually do this import Spydev and start using their library. So the basics are you create a Spydev instance, then you need to open it. And so this has a couple options. So there's a port and a device. And this comes back to the two devices we saw here. So there's Spydev 0.0 and 0.1. And so this first number is the port, which is just an indication of, a device might have multiple SPI buses or channels that it can talk to. The Raspberry Pi just has one that's exposed to users, and so that's basically Spydev 0. And then the second number after the dot is the device. And so remember, like I was saying, SPI has a concept of a chip select line, and so the Raspberry Pi has two different chip select lines for its hardware SPI interface. So there's CE0 and CE1, and with those two lines, those just correspond to the device numbers here. So device number 0 is going to be CE0, and device number 1 will be CE1 when it's connected to the Raspberry Pi. So it's important to make sure you've got the lines correct. Check out the Raspberry Pi GPIO diagram. There's tons of them online, and you should be able to see where the CE lines are for that. And make sure you've got, if you've connected to CE0, that your code will actually specify that. So this code, it's saying, okay, use port 0 device 1. Well, in this case, my MCP chip I'm actually talking to is on device device 0, so it's on CE0. So I'll change that. Now it goes into a main loop here, and let's see, actually let me just fix up some of the spacing here that kind of got mangled. And so now we've got a while loop, and actually let's put some spaces in here too. And we don't need that. So so we just have a main loop, and this is just going to send a transfer request. And actually, let's not start with transfer. Let's start with like a read. Let's start with a read bytes command. So let's go back to the little SPI reference here and see kind of what are all the functions we've got that we can call. So there's a read bytes, which just takes in how many bytes to read, and it's going to return back an array of the byte data. So let's go back and let's actually call read bytes, and let's just read 2 bytes of data, and that's going to give us a response. Now let's print it out. So let's print out received OX, and let's see, I'm going to use let's use the bin ASCII library. So this is always a nice library. I think I mentioned this before. So there's the bin ASCII.hexlify is a fun little thing to use. So let's do bin ASCII.hexlify my response data. I think this will work. Sometime I think hexlify wants a byte string. We'll see if this gives an error. I'll show you how to fix that. That's one murky area of Python, unfortunately, is especially because it changes between 2 and 3. How do you interpret an array of bytes. You know, it's in like C, you can just have an array of uint 8s. In Python, it has a concept of strings, and strings might be Unicode, and you don't care about Unicode in a lot of cases. And so I'll show you a little bit about how to deal with that. There's basically a byte array class that means a list of bytes, and it shouldn't be interpreted as a string. I mean, it could be if you encode it or decode it the right way, but that solves a lot of problems as far as, you know, in a lot of cases, sometimes in Python, especially Python 2, you get back data, and if it has Unicode in it, it might explode, and you might not even, it might inadvertently have Unicode, like it might have, you know, some byte that's higher than 255. So it's a little bit of a murky area. Even I don't understand it all fully. There are some good talks I think I've seen that try and break down the Unicode mess, and it's getting better. I think Python 3 is kind of where they've fixed things. So okay, let's delay for I don't know, let's delay for a second. So we'll do that. And then this is just a little accept to see when we catch, if I control C out of this. I'm going to change this, so let's make this a finally, because this will just ensure that no matter what happens, if I control C and that throws a keyboard interrupt exception, then this close is going to be called, or if like an error occurs, you know, this finally clause is going to be called and this close will be called. It's good to close the SPI interface. It's not the end of the world if you don't, because when your program exits, it's going to close those connections. And really, the only thing that's open is just that /dev/Spydev device. So, you know, it's really just an open file. But it's good. It's especially good practice to always be in the habit of being conscious about the resources you're using and making sure to clean them up. So, okay, let's save this. Oh boy, wow, that was a little funky. Normally I press, I see what it is. So this little bit of transition on my Mac, I have to press the Option key to save things. On Linux, it's Control, so I'm sure I'll have some fun with that. Okay, now let's run this thing. Let's go back, and this is probably, it might error out because of that hexlify thing, but let's just see what happens. So Python, spy test, and let's see. Yep, so like I thought. So tell me, must be a string or buffer, not a list. Basically, this bin ASCII.hexlify. It's right now it's getting a list of bytes, but it expects explicitly either a string or a buffer, and I'll show you how to fix this. Just take that array of bytes and turn it into a byte array, and so basically the byte array is a class in Python, and it just gives you a buffer of bytes that's like a string but not always interpreted as string data. And as its initializer, it can take in a list of data. And actually, man, here, how about this? Make it a little more obvious. Let's just print out what we get back directly. Let's just print out the response. And we should see that this is actually a list of data from Python. So yeah, so you can see this is coming back as 2 bytes, and it's reading nothing. It's getting 0, 0. And now if I actually use the bin ASCII function, so that byte array is being passed that array of bytes. Now it creates a byte array with that value, with those values, and then, oh sorry, I don't want to do byte array here. I want to do byte array before I call the bin ASCII function. So let's do byte array. There we go. We get all the parentheses right. So I take that array, turn it into a byte array just to make hexlify happy, and then I call bin ASCII.hexlify, and this should print out in hex the output that I got. So let's do this. Oh, did something wrong. Oh, I'm probably missing a parenthesis here. Yep, I am. There we go. And let's do this. So now you can see, okay, OX0000. So it's reading back zeros here, which is good. So this is, you know, really simple. Now, unfortunately, in order to get some output from this chip, I actually have to send it something. So maybe we'll try that in a second here. But let's look at this on the wire with the Celia just to make sure that everything's kind of working. So actually here, let's run this thing again, and then let's do a quick little capture. So we should see a few instances of this. So yeah, there's a couple instances, and let's just kind of dive in here. And so like we saw before, the chip enable line gets pulled low, the clock cycles a lot. Now the output from the device down here, it's, you know, it's not sending anything. So we'll see as we kind of send and receive data that it's responding here. But that's kind of cool. So that's kind of showing, okay, here's the default mode of 0. Let's play with the SPI modes a little bit and see how things change. So let's save this capture. Let's call this read mode 0. Okay, now let's change, and let's go back to the documentation here. So the mode is a parameter we can change on the Spydev device. And this, you can set a value from 0 to 4. And this just changes how the polarity and the phase are interpreted. So let's change this to like a value of 1 and see how things happen, how things change. So to do this, you just need to change the SPI mode. So like, let's set this to 1. By default, it's going to use 0. So let's save this, and let's see how things change when I rerun the program. So now I'm running it, still getting 0 back, but that's okay. And we go back to the Celia, and let's do a new capture, and we should see some differences. So we zoom in here. Oh, we might actually not see a difference in this one, because I kind of forget offhand how all the different modes map here. So let's go back to Wikipedia and see what the polarity and the phase, how these change. So, okay, so a value of 1, here we go, SPI mode 1. So my polarity is going to be 0. So polarity, that's what controls whether my clock is active high or active low. And then my clock edge, like when I'm sampling things, that controls the phase of this. So okay, so in SPI mode 1 I have the exact same polarity, so we're not going to see difference. So let's change it to SPI mode 2 and see how the clock changes in this case. So let's go back to the code, and let's change this to SPI mode 2. And now let's run this. And so now let's run a new capture. And we should see the clock should be different. Oh, already I see a difference. See, the clock line here is high, whereas before it was low. So that's kind of telling me that the clock is staying at a normal state. Now it looks like I see a little red dot, and that's probably the Celia. The logic analyzer is a little confused now because I've told it that in the protocol analyzer that my clock is low when inactive. Let's change that. Let's say it's high when inactive. I probably have to capture again for it to reinterpret this. Oh no, it actually looks like it just worked. So okay, now we see a difference here. Like, look at the clock line. So remember, this is the read from mode 0. We can see the clock is low, and then it jumps high when it's active. And here's with mode 2, we can see it's high when it's active, and it's low, it's high when it's idle, and low when it's active. So you kind of see the difference in how these modes operate, and it actually changes how things change over the wire here. Now the chip select line, I can't remember. Let's see. I think we can control whether that's yeah, here we go. So there's this CS high property. So this controls if the chip select is normally, if it's active high or if it's active low. And let's just check and see if there's anything else. Okay, yes, so there's just CS high. I don't think they have a CS low parameter. Yeah, so let's set CS high to true. So this should tell us, because right now we're seeing in the logic analyzer, the chip select is active low. So when we're talking to the chip, it's pulled low. But if I set CS high to true, this should invert. We should flip this around. So let's check that this actually works. So we'll do SPI CS high equals true. Oops, and let's save that. And now let's run this. And okay, so we're running, and let's do a quick little capture. And okay, yeah, now it's different, so we can see we're low. And if we zoom out and find our data, kind of zoom all the way in here, and yep, it looks like it changed. So we've got, we're idle low now on the chip select line, and then when it's active, it jumps up high. Versus, when we saw in mode 0 with this chip select, it was idle high and then active low. So something to be aware of. And again, you're going to want to check your chip's data sheet. It's going to differ by, each chip is sometimes different. Most chips, the standard usually is that you pull your chip select down low to be active, but it's different for different chips. So something to be aware of. Okay, so those are a couple knobs that you can tweak. There are a few others, and maybe I won't show all of these. So you can control how many bits per word. Basically, you can change to either, do you want to send things a byte at a time or a word at a time, like 2 bytes at a time. And again, it just comes down to what chip you're talking to and how it likes to interpret the data. Let's see what else is here. The LSB first, MSB first. This controls the order of bytes that you're sending. So actually, we can see this in a second. Let's do some writes. So let's update our program, and we'll kind of play with some of these parameters. So instead of read bytes, let's do a write bytes. And let's look at the little docs here on this. So this takes in a list of values, and so this is a list of bytes that we want to send in. And so let's send 2 bytes. Let's send OX, how about 42, and OX01 maybe, something like that. So okay, so we'll send 2 bytes, and there are a lot of ways you can do this. Like you could send an array like this. You could create a byte array object and pass this in. I think this will work. Again, it's kind of this murky area of Python. Sometimes things are written to expect arrays of things. Sometimes they expect strings. Sometimes they expect explicit byte arrays. I like the byte array just because it's the most explicit thing. Like it's showing my intention that this thing is a list of bytes. Don't necessarily interpret it as a string. You could if you like encode it or decode it as Unicode or whatever, but it's really just bytes. So I like to be explicit. But let's just do this. We'll keep it simple. So okay, let's save this and let's run our program. And now let's do a little capture. Oh, interesting. None type is not. Oh, duh. So obviously the write bytes function is not going to return anything, and we should actually be able to see in the docs here. I don't think it mentions anything. So yeah, returns nothing. So obviously I need to change this code a little bit. So let's just delete that and comment that out. Okay, so now let's run this thing. And we won't see any output, but it should be running in the background. So let's do a quick little capture and see kind of what changes. So zoom out. And we can see, okay, now we see some stuff going on. So, we have the modes kind of set in a funky way like we had before. So, the chip enable is active high now, and the clock is active low. But now we can see, okay, the Mosey line, the Raspberry Pi output, has some data on it. And let's change our SPI Protocol analyzer here. So let's, oh, this is where we change it to hex. There we go. I've been looking for this setting. So, okay, so let's change things. So most significant bit first, that's standard. 8 bits, that's standard. So the clock is low when inactive, and your enable line is active high. That's how we have things configured right now. Let's see, what is this thing? Oh wait, did I get that right? No, sorry. The clock is high when inactive. There we go. Save that. There we go. Okay, cool. So look at that. We can see now we've actually got some data that's interpreted. So this OX42 down here, that's data that was observed being written out by the Raspberry Pi, and OX01, which matches exactly what we had. So that's kind of cool. So we can see these things working. So let's play with that MSB LSB bit. So if we go back to the docs on this, so there's a little boolean here called LSB first, so least significant bit first. So it's a boolean. The default is I think the default is true. I want to say, let's see. No, sorry, it's false. Well, let's actually see what is the most significant bit that's coming back for this. So if I go back to the capture here, so for 42, if I run a little calculator, let's actually see what this looks like and what the bits are set. So we go into hex, and we put 42 in here. So okay, so yeah, so here's the most significant bits up at the top. So it goes 0, 1, 0, 0, and that looks like, yeah, so we're going most significant bit first. So 0, 1, 0, 0, 0, 0, 0, 1, 0. So that's the default, is so LSB first is false, is the default, it looks like. So let's set this to true and see what happens. We should see this inverted. So let's set spy.lsb first equals true, and let's save this, and let's run this now. And we'll go into, what's this mad about? Invalid argument to sleep. I must have, did I put in something incorrectly here? Let's make sure I got this thing named the right thing. So, yeah, LSB first. That's a little funky. Did I put in too much white space or something somewhere? Let me let's just comment this out. Just make sure that this is right. Okay, that's really weird. I've never seen that fail in that way. Let's cancel this. Let's see what's going on here. So, okay. So I want to set LSB first equals to true, and I don't see anything wrong with this line. That's interesting. Huh, that is really interesting. Invalid arguments for this. Maybe the Raspberry Pi hardware doesn't support this mode. This is, I actually haven't really tried it, so something to be aware of, that maybe this doesn't actually work with the hardware SPI. I'd be surprised if it doesn't support it, but that's a little funky. Maybe something to look at later. But again, this just comes back to, these are all the different options we can set. We can change the speed. Let's try changing this and see how the clock speed changes. So just for now, let's see what the clock speed is that we're using. So looks like it's about 300 kilohertz. So let's crank this up. Let's set this to a high speed. So let's what is this thing called? It's max speed hertz. Okay, so max speed hertz, and let's see, can we do 10 megahertz? So 1 2 3 1 2 3, and let's see what the Raspberry Pi can do. So we'll save this, and let's run this. And okay, so it should be running. So let's do a little capture. And now let's kind of zoom out. Let's see how the clock changes. So if I kind of zoom in here, and we should be a lot faster. Oh, interesting. Wow. So it's looks like 3.33 megahertz, and you can see it's not that nice of a clock. This thing is kind of all over the place. Oh, well, duh. I'm sampling at 10 megahertz, so of course I'm not going to see this thing. Let's crank this thing up to like 50 million samples per second. So that's a good old Nyquist, where you can't recreate a signal if you're capturing it at the same rate. So you need to capture at least double the rate of your signal in order to see it. And so we can actually see, like, we're getting this funky signal where, like, the clock's not matching up, it's not doing 8 bits. That's because we're not sampling it the right way. So a little thing to run into. Okay, so let's run this thing again, and now we should be able to see the signal. Zoom out, and now we should see a nice clock, and yeah, it's looking a lot better now. So okay, 6.25 megahertz, and actually I remembered that I think that is the limit for the Raspberry Pi, the hardware SPI interface. Without I'm pretty sure there's like some kind of wacky device tree setting you can change to crank this up a lot higher. But in most cases, you can get up to like 6 megahertz, which that's pretty quick. Like 6 megahertz, that's at a point where, like, you can't toggle an I/O pin on the Raspberry Pi at 6 megahertz. I mean, you can in some cases, but you really can't do much. So this is, one benefit of using SPI is that you can do really fast things. And this does matter. Like, for a little ADC like this that's 10 bits, okay, sure, we don't need to talk to it at 6 megahertz. But, imagine an LCD device, like a TFT display, and when you need to send, thousands and millions of bits of data to update the entire screen, changing that clock rate to, high megahertz rate makes a big difference, and, you can see dramatic speed increases for it. So, okay, cool. So we can control the clock. That's pretty much all the different settings we can change here. So we saw reading bytes, writing bytes. I'll do the transfer functions now, and so let's try. So transfer and transfer to. Let's start with transfer and kind of see how this works. So let's change this to what we had before. So we want to say our response equals, and then let's call xfer. And so, like I said before, transfer is going to write out 0x42, 0x01, and at the same time it's going to be reading in 2 bytes of data. So it reads in exactly as many bytes as you write out, which in a lot of cases, like, you sometimes might need to write out, you know, like dummy data. Like, let's actually write out 3 bytes. You know, so imagine a device where, like, I need to write a couple bytes to tell it to start, and then I need to read a byte after that, in which case I just need to clock out like a dummy byte of 0 to make sure that I read that data. So let's save this, and let's see what this does on the hardware here. So let's run this, and let's do a little capture. Yeah, good, it's running. And now let's zoom out. Oh, and sorry, I should actually print out what we're doing. So let's uncomment this line, and let's save this, and let's just run this again. And so now we should see. So you can see there are 3 bytes that it's returning. You know, there's 2 hex characters in a byte. And so that's because I did a transfer of 3 bytes, so it's sent 3 bytes, and then it's also receiving 3 bytes, and I'm printing out the results here. I'm not getting anything back just because, you know, I'm not talking the right format to this ADC, but it doesn't really matter. We can still look at it on the wire here. So let's do another little capture of this. And we really won't see much difference here because our chip isn't responding to what we're sending. But we can see at least that we're sending the data again. So 4201 and then 00 again. So it's exactly what we sent. Now the interesting thing here, notice the chip enable line up at the top here. It's held active the entire time that this transaction happens. Let's change to a different function. So and let's kind of read what these functions. So the xfer function is telling me the CS line will be released and reactivated between blocks. Delay specifies the delay in nanoseconds between blocks. So I'm trying to remember. I believe a block is how many bits per word. Like, you know, it's saying it should be set up by default. So if between each byte, it should be toggling the CS line, and that's the difference between the xfer2 function, where this is actually just going to hold the CS line. Now the interesting thing is, I actually don't see that in the Celia trace here. Like, you know, in between these 2 bytes, I don't see any difference here. So I might not be interpreting this correctly. It's not something that we commonly use. You know, in most cases, the chip enable line is just always held high and low. But I don't know. Let's just try. Let's see if I can actually see something change. So tell me there's a delay parameter I can change in here. So let's try that in nanoseconds. So let's do a lot. Let's do like 1,000 nanoseconds. So let's save that. Let's see if this changes anything. So we'll run this. And oh, that's weird, huh? Maybe these docs are out of date. So when the documentation fails, let's just jump down to the source real fast. Let's look at xfer. So let's go down to xfer, and we should see. Okay, here it is. So what's it doing? Is it parsing out? Okay, so it's parsing out an optional integer, delay usex. Maybe I have the name incorrect. Delay microseconds. Yeah, this should be. Oh no, interesting. It's you can actually pass in like the speed in hertz and the bits per word. Wow, I didn't know that. That's kind of interesting that you can explicitly say during the transfer how you want to configure the SPI interface. That's kind of nice. Okay, so I must have this named incorrectly. So it might be delay underscore nanoseconds. So let's try this. So unfortunately that document seems to be out of date, but yeah, that's just unfortunately the fact of life. So no, it takes no keyword arguments. Boy, that is really bizarre why that's not taking that argument. So I must be sending this in the wrong order here. So, well, anyways, you know, I was hoping to show kind of the difference between these 2 functions, but you know, I'm not really seeing a difference. Like, let's just try it. Let's call the other function transfer2 and see if we see any difference here. So let's get rid of that, and let's just call xfer2. And oops, press the wrong button. There we go. Save that. And let's run our script again. And okay, now we're getting data back. So let's take a look on the wire, how things look. And let's see if the chip select line changes. So yeah, I don't see any change here, unfortunately. So that's a little weird. And it's also weird, I don't know what, that's kind of bizarre. We've got a little blip over here that it cycled. Maybe I'm actually interpreting this the wrong way. I didn't do enough homework on this part. It could be, I have a feeling perhaps maybe it's like in between, maybe it's in between transfer calls it's changing the chip enable line. Not totally clear on that. So, you know, it's something you're probably gonna have to look more into the docs to see. But those are really the core functions. Like you can write data, you can read data, or you can transfer data, like read and write data at the same time. And so when we saw earlier the trace of reading data from the ADC, and actually here, let's just go back and run that script again. That was using the transfer function because it was reading data and writing it at the same time. So if I run that simple test, and so now that's reading the ADC, and I should, so that's kind of interesting. I think I have the Raspberry Pi hardware in a weird SPI state because I was messing with the SPI device. So I've probably changed like the polarity and things. Although it's interesting, my code should be setting that back to normal. But let's just capture it. Let's just see what happens. But I have a feeling that things have, like you can see now, for some reason it's stuck in the mode where the chip enable line is active low when it really should be active high. Or sorry, it's active high when it really should be active low. So I've kind of gotten in a bad state now, which. That's a bug. My code should be handling that, but so you can kind of see it's all funky now. But ultimately, the code for this is just using that transfer function, like we saw kind of documented here. So, you know, read, write, and then transfer. Those are your main operations with the SPI bus. And then real briefly, we're maybe kind of running a little bit longer on time. So again, like I2C, I was kind of wondering, how is this stuff implemented at a kernel level? Because, you know, this module, although it's really nice and it's maintained and, you know, the code is up on GitHub, you have to compile a native extension. Luckily, this one does support Python 3, which is pretty nice, so that's not too bad. But, you know, if I want to make a pure Python version, I wanted to look and see how does this actually work at a kernel level. And just like we saw with I2C before, go to the kernel.org, Linux kernel documentation, and you can find all kinds of documents on the Spydev, S-P-I-D-E-V, the Spydev interface. And that's what really is happening behind the scenes with all of these libraries. So like we saw that those Spydev devices, this document tells you how to interact with these devices. So you can open them as a character device. You can, when you write data to these devices, it talks about how it will use that as just a SPI write. If you read data, it'll do a SPI read. And then to do a combined read and write, you have to go back to our old friend, the IO control function. And so this explains how to set up those IO control functions to do like a transaction that reads and write data. There's IO control functions it talks about to set the SPI mode, to set the SPI bits per word, like all of that stuff that we saw exposed by the Python library. Underneath the covers, it's really just making these IO control calls, and it's actually the Linux kernel SPI interface functions that are calling this, and then the Python code calls that SPI interface. But again, I think, you know, it's definitely feasible. I can do IO control functions again. I don't have examples of them yet for SPI, but ultimately I want to do in this little pure IO library a version of Spydev that has the exact same API. So like we saw, you know, I'll expose all of these same functions, but have it implemented by doing the raw IO control calls. And then that way it's nice in that it's a pure Python function. Like it's the exact same problem as the I2C where, you know, I'm not calling a C extension, so it's easier to install, but it's a little bit slower because Python has to do all of this data marshalling as far as like, you know, getting memory into the format that the C functions expect, and then pulling it out of that format and putting it into a format that Python likes. There's a little bit of overhead there. But I think it's a good trade-off in that now, you know, libraries can depend on this and they can just do a pip install. You won't have to compile a Python extension, and it's all kind of ready to go in that regard. So Otherwise, I think that was it. If folks have questions, then maybe feel free to throw them in the Twitch chat, and maybe I'll jump back to the fun little, here's the crazy matrix view. So yeah, that was kind of the deep dive into the SPI, the serial peripheral interface. And again, it's very similar to I2C, and it's a way for two chips to talk to each other, but there's some big differences. So there are 4 wires that you need here. There's a clock line, a data output, a data input, and a chip select line. And unlike I2C, all of your devices can't share the exact same line. So like each device needs an individual chip select line. They can all share the same clock, data output, and data input, but they have to have a unique chip select line. And then the other big difference is that the speed is something you can control with the SPI interface. So you can crank it up to many megahertz as fast as the hardware supports. One brief thing that I didn't mention, but the SPI protocol, as we saw, is pretty simple. Like you're just toggling clock and enable lines. You can actually do that in software. So like a lot of our Arduino libraries we have a software SPI implementation. I have a little software SPI implementation I did in my main Python GPIO library. And that's useful because now you can use any 4 GPIO lines. You don't just have to use those hardware SPI lines on the Raspberry Pi. And so that's a good way where, like, if you have 2 chips, and this is a big problem sometimes, especially with Arduino, you want to read like from a micro SD card, which uses a SPI interface, but then you also want to talk to a sensor that uses SPI. And if they don't use the same mode and polarity and clock phase, then when you try to talk to one and you get that wrong, it's not going to understand what you're saying. So in a lot of cases, it's easier, instead of trying to constantly change the polarity and phase and things like that, to just say, let's just create a whole new SPI bus. It's got its own clock, phase, and polarity, and it's easy to do that with software SPI. So it's just something to think about. You can bit bang this protocol, effectively emulate it with GPIO. And it's not as hard as you might think, because you really just have to toggle the pins and toggle the clocks and read and write data for it. So yes, like we saw, there's the Python Spydev is the library. It looks like it's pretty well maintained now. And at a low level, if you really want to get in there, check out the Linux kernel documentation. So I think that's it. I don't see a lot of questions, so we'll wrap this up. Thanks everyone for watching. Hoping to make this kind of a weekly thing. I don't have a fixed time yet, just because it takes so long to get this streaming set up that I want to get this process to be nice and smooth and just flip a switch and it's on and ready to go. And so hopefully then we'll see a lot more streaming after that. But it's getting there. It's getting a little bit easier. And hopefully the quality looks good, and the audio sync hopefully is working well too. And I'll upload this to YouTube. And so check out the Adafruit YouTube channel. Subscribe to that. You'll see this video, lots of little project videos. Check out the twitch.tv/Adafruit channel, and that's where I stream this live, and you can watch all kinds of other live streams. There's stuff like the Desk of Lady Ada that's happening. Noah and Pedro have some 3D stuff that they like to stream, so check that out. And speaking of the Desk of Lady Ada, if you tune in tomorrow, I think Lady Ada is planning the last live stream for the Pi Zero contest. So I think tomorrow evening sometime, might look for that and kind of see what's going to happen. What's the number 10 stream going to be? So that's it. Thanks a lot, everyone, for watching. And quick shout out to Cool Retro Term, which is kind of the program in the background there. That's pretty awesome. And then the intro video I had before, got some like NASA shuttle stuff there. I'll have a little proper kind of credits thing at the end. I'll put that in there too. But everything's kind of fancy, and I've just built this on top of other cool stuff that people have done. So awesome. Thanks a lot. We're gonna end the stream, and see you guys in a week.